We went through a rather rigorous quadratic formula number crunching event. And some of you are thinking, after all the trouble we went through to solve for x, it didn't even make, x wasn't even big enough that when we subtracted it from the original concentrations of our reactants to change those concentrations from what they were initially in terms of reporting with the precision that we're allowed to because of significant digit protocol. You may be asking yourself, if it didn't make a difference, is there an easier way to solve for x that maybe we can bypass the quadratic? And there is. And here at Ontario High School, I allow students to use something called the 1% rule to determine whether they need to use a quadratic or not. I offer this caveat to you. I will demonstrate this, but you will need to speak with your own instructor if you're not an Ontario High School student and ask them whether they will allow you to use this rule. It's really up to your instructor, and please check with them. You'll notice the problem we're going to use to demonstrate the 1% rule is the one that we've been using, sample problem E. So follow through and see how we do this. And again, if you're not an Ontario High School student, please check with your instructor before you use this. Kc for this reaction was small, 1.2 times 10 to the negative fourth, in comparison with the initial concentrations of the carbon monoxide and the chlorine, which were 0.4 moles per liter and 0.5 moles per liter respectively. When the value of K is very small in comparison with the initial concentrations, the assumption can be made that the initial concentration minus X is essentially equal to the initial concentration. There is no significant change in the initial concentrations. So here's how you use the 1% rule. You're going to divide the value for K by the initial concentrations and then multiply that quotient by 100 to determine the percentage. If the percentage is less than 1%, it's safe to assume that the equilibrium concentration is essentially the same as the initial concentration. So for the carbon monoxide, we're going to take 1.2 times 10 to the negative fourth divided by the 0.40 moles per liter. We'll multiply that quotient by 100, and it gives us an answer of 0.030%. For the chlorine gas, we have 1.2 times 10 to the negative fourth divided by 0.50 moles per liter. We multiply that quotient by 100 to get 0.024%. So the assumption that the molarity at equilibrium is equal to the molarity initial molarity, that assumption is valid in this case, and that's the application of the 1% rule. If it's 1% or greater, go ahead and use the quadratic. If it's less than 1%, you're relatively safe. Now, when we set up our ice chart using the 1% rule to determine whether we're going to use a quadratic or not, essentially the change here is we're going to assume that the 0.40 minus x and the 0.50 minus x are 0.40 and 0.50. So at equilibrium, we would have those same concentrations, 0.40 moles per liter of carbon monoxide and 0.50 moles per liter of chlorine. Then our concentration of COCl will still be x, as well as our concentration of Cl will be x. We're going to solve for x as before, except now because we don't have a need to use a quadratic. We can solve for this relatively simply. So as we continue looking at solving for x, we're going to take our K sub C value, 1.2 times 10 to the negative fourth, write the equilibrium constant expression for this, making it equal to the concentrations of COCl times the concentration of Cl divided by the concentration of CO times the concentration of Cl2, using the values that we have from our ice chart. We have x times x on top divided by the 0.4 moles per liter CO times 0.5 moles per liter Cl2 on the bottom, and that will simplify to x squared divided by 0.20 moles squared per liter squared. Now, the final solution for this is to take your 0.20 moles squared per liter squared and multiply both sides of the equation by that, so it cancels off of the right side of the equation, and the left side of the equation would then have 1.2 times 10 to the negative fourth times 0.20 moles squared per liter squared. And if you then square root both sides of this, and that's what I show here. I did not show that intermediate step, but that's what I did. But now we have the square root of the quantity 1.2 times 10 to the negative fourth times 0.20 moles squared per liter squared is equal to x, and our final value for x then is 4.9 times 10 to the negative third moles per liter. We can now go back to our original ice chart and plug in our final equilibrium values. We're going to be adding 4.9 times 10 to the negative third moles per liter to the 0 moles per liter that represented the initial concentrations of COCl and Cl respectively. And so our final concentrations at equilibrium are the 0.40 moles per liter for CO, 0.50 moles per liter for Cl2, 4.9 times 10 to the negative third moles per liter for COCl, and 4.9 times 10 to the negative third moles per liter for Cl. The value of x using the quadratic equation, the solution was 4.8 times 10 to the negative third moles per liter, using the assumption that the 1% rule allows us the value was 4.9 times 10 to the negative third moles per liter. So very, very close. And again, check with your instructor before you use something like the 1% rule, but it's valid for use at Ontario High School. Well, we've been through a lot, but we're still not done with sample calculation E. The last part of this is to find K sub P. So we're going to use that equation that we used before. K sub P is equal to K sub C times the product of RT raised to a power of delta N. In this case, delta N is equal to 2 moles of gaseous products using the stoichiometric coefficients minus 2 moles of gaseous reactants using the stoichiometric coefficients. So 2 minus 2 is equal to 0. You know from your math classes that any quantity raised to a power of 0 is equal to 1. So in this case, RT raised to a power of 0 is equal to 1. So Kp would be equal to Kc times 1, which means that Kp is equal to Kc. So Kp would be equal to Kc, which is 4.9 times 10 to the negative third. The quick rule of thumb for this is if you have stoichiometrically equal in terms of the coefficients of gaseous products add up to the same number as the coefficients of gaseous reactants, then Kp and Kc will be the same magnitude, same number. Now, one more calculation that we're going to do, sample calculation F. We're going to use the same reaction we've been using, where we have the carbon monoxide gas plus the chlorine gas is in equilibrium with COCl and with Cl gases. Our K sub C for this is 4.9 times 10 to the negative third, and we want to find what K sub C would be for the reverse reaction under the same temperature conditions. So if we flip this reaction and started with COCl and Cl as our reactants forming CO plus Cl2, what would K be for that? And here is one of the things about equilibrium that is real good to know, is that K for the reverse reaction is equal to 1 over K for the forward reaction. Again, forward's going right as you look at the reaction, reverse is going to left as you look at the reaction as it's written. So the K reverse will be equal to the inverse of the K forward. So you just take 1 divided by K for the forward value for the forward reaction. So 1 divided by 4.9 times 10 to the negative third gives a K for the reverse reaction of 204. Here are some undeniable truths about the equilibrium constant K. K values greater than 1 mean that the forward reaction is favored in the equilibrium system, meaning the products are favored. K values less than 1 mean that the reverse reaction is favored in the equilibrium system, which means that the reactants are favored. At equilibrium, rates of the forward and reverse reactions are equal, not concentrations, but rates. We've explored a number of different types of problems that are associated with equilibrium, and now it's time for your turn. We're going to offer you several problems and have you do them, and what I would recommend that you do as we look at this problem and go to work through it, just pause the problem on this slide, work the problem out on your paper, make sure you have a good calculator at home, and work through the problem. And then when you're done, resume the podcast and I'll show you the answer that I got, and hopefully our answers will agree. So the first problem, we're going to look at the equilibrium system that involves hydrogen and iodine gases forming hydrogen iodide, and this reaction will reach equilibrium with these concentrations: 0.12 moles per liter of hydrogen, 0.020 moles per liter of iodine, and 0.56 moles per liter of hydrogen iodide. The goal here is to find the equilibrium constants Kc and Kp for this reaction. So go ahead and pause and work this out, and we'll resume here in just a couple minutes. Welcome back. Let's see how you did. The most important thing that you can do when solving any equilibrium problem is to write the equilibrium constant expression. Here, because you're given the concentrations in moles per liter rather than pressures, we'll go ahead and write this as a Kc, or K sub C, and it's equal to the concentration of hydrogen iodide squared divided by the concentrations of hydrogen times the concentration of iodine. We then substitute in the moles per liter concentrations of each of those. So you have 0.56 moles per liter squared divided by 0.12 moles per liter times 0.020 moles per liter. And our value for Kc is 130. Now, the equation that we use to convert from Kc to Kp is that Kp is equal to Kc times the product of RT raised to a power of delta N. And before we even write that equation down, we can find delta N, because if delta N is 0, then Kc will equal Kp. So we add up the stoichiometric coefficients for the gaseous products and then subtract from them the stoichiometric sum of the coefficients of the gaseous reactants. In this case, they're both 2. So delta N will equal 2 minus 2, which is 0. And in that case, where delta N is 0, then Kc will equal Kp. This is the end of part 1-6 of the Ontario High School video podcast series having to do with equilibrium. I want to leave you with a quote by Mark Helprin from his famous novel Memoir from an Ant-Proof Case. "When faced with something I fear, I tend to eat spaghetti." I wish you well.